Hello everyone. We are starting a free open lecture on Discord. Our lectures are held weekly. If you are simply a viewer and want to ask your question and get an answer, join our lectures. You can find the link to Discord in our Telegram channel, where you can also find out the schedule for the lectures. Join us. We have set the task. Now let's solve it. Look, first I will rewrite this problem in vector form. Let me explain in detail. Firstly, this problem in vector form. Here, I simply multiply v1 by the numbers 1, 2, 3, and I can say that I multiply v0 everywhere by 1s. Here it's 1, here it's 1, and here it's 1, indicating the same value in each position. In vector form, which is a mathematical representation of quantities, this will look as follows. v0, a constant term, multiplied by the vector 1, 1, 1 plus v1, a coefficient, multiplied by the vector 1, 2, 3. Here I have the vector r1, r2, r3, equal to the vector 0, 2, 3, representing specific values in a sequence. Now I will basically introduce the notation. Since we are looking for v0 and v1, I will denote them using the vector x. Vector x. This is a vector which has two distinct components, namely v0 and v1. Now this vector that is on the right side of the equal sign, I will denote it as vector b, slightly. This will be the vector 0, 2, 3. I will denote r1, r2, r3 as vector r. I will denote r1, r2, r3 as vector r, r, r. And I will write these vectors 1, 1, 1, 1, 2, 3 in the form of matrix A. That is, I will basically have matrix A, where essentially the first column is a vector of ones, and then additionally, the second column is actually just simply the vector 1, 2, 3. Now, introducing these notations, this was system 2, this is system 3. I will move on to system 4. Systems 2, 3, and 4 are all the same. It's simply just another notation system. What exactly do I get? I multiply v0 by this vector, and I multiply v1 by this vector. This can be written as the matrix A multiplied by the vector x, which is a fundamental concept in linear algebra.
Want to become a great programmer? Subscribe to our Telegram channel.
That is, I multiply the row by the column. I get b minus 1, b plus b minus 1, so I have b plus b minus 1. Then I multiply the second row 1.2 by the column. I get 1 v0 plus 2 v1, so I have 1 v0 plus 2 v1. Then I multiply the third row by the column. It turns out to be v0 plus 3 v1, as expected, so everything is fair here in this case. We wrote this part as x in the equation. Next, adding vector r equals vector b, respectively. Here we have rewritten our system in vector form in a more efficient, concise, and more streamlined manner. Here we have A, which is a matrix with 3 rows and 2 columns, that is, a 3-2 matrix. The vectors r and b. These are vectors in 3-dimensional space from the space R3, meaning they have 3 real components. And the vector x is a vector which is from the space of R2, meaning it has 2 separate and distinct real components. Additionally, I have written the vectors here and here once again. I emphasize that this is specifically a vector from R3 and R2. From now on, I will stop drawing these arrows at the top because otherwise I will introduce additional notations later to avoid confusion. So I will write X, R, and B, but remember that these are vectors. Remember what problem we are solving. We need to choose. These are in such a way that the sum of their squares is reduced to the lowest possible level. And with these values, we will find not V0, but the vector X, because X consists of these numbers. We need to do this in a manner that is appropriate and accurate. Now the length of the vector, that is the norm squared, is the length of this vector R. How is it calculated? As you know, the distance or length of a vector, it can be calculated using different formulas, each with its own unique approach. I will define it, as you can easily guess, as R1 squared plus R2 squared plus R3 squared, which is a common method used in various calculations. I remind you that this particular thing should indeed tend to the minimum, and here is the root of the problem. This specific thing should actually tend to the minimum. So what do we have right now? Well, let's just take a closer look at this particular equation. And let's draw a few more pictures to better understand exactly what is happening here in detail. For this, we need to recall a little bit more of what I told you about linear algebra. And look, specifically, I want to consider the product of matrix A and the vector X. Specifically, vector X is a vector in the space of R2. That is, I have some two-dimensional space R2, and in it lives the vector X. Next, I multiply the matrix. I then apply the matrix to this space R2. In particular, I multiply it by this specific vector X. What happens to the entire space and to the vector X? This entire space transforms from two-dimensional to three-dimensional because the matrix A has 3 rows. There is actually already a space here, indeed. R3. And the vector X itself, which is a two-dimensional vector with some 2 components, transforms into a three-dimensional vector. I will refer to it as X. Moreover, pay attention. This is in such, let's say, a general case. If we consider our specific matrix, which is 1, 1, 1, 1, 2, 3, how exactly is this space indeed formed? It must be in the space R3, essentially R3. How do I get this vector Ax from the vector X in order to obtain the desired result? I simply multiply the first component by the first column and plus the second component multiplied by the second column. In other words, the three-dimensional space, denoted as R3, is spanned or generated by the linear combination of these 2 specific columns. This situation represents a more general and broader case in the context of linear algebra and vector spaces. Let's take a moment to carefully consider our specific case in detail, examining all the relevant factors and nuances involved. I have vector 1, 1, 1 and vector 1, 2, 3. And the vector 1231. Consider the numbers 2, 3, and some vectors similar to this. These elements are key to understanding the concept. And any vector X, what is that? It is their linear combination. And what, tell me, does the linear combination of these 2 vectors form? I will remind you that the third vector and the set of all these, third vector, set of all these linear combinations, got space, a plane. Yes, it will indeed be an airplane that is actually situated on these 2 vectors. In other words, in R3, these 2 vectors essentially define a plane that is spanned by these 2 vectors in 3-dimensional space, basically. And accordingly, when I apply the matrix to any vector X, I do not get an arbitrary vector from R3, but rather a vector that lies in this plane. Such a space is often referred to as the column space of matrix A. It is denoted as column. That is, col comes from the word column, which means column, the column space of matrix A. This is, in other words, the linear span. You can use English terminology, for example, say span, linear span, or just curly brackets without it, which means you have several options. The word is to simply draw the vectors 1, 1, 1 and the vector 1, 2, 3, basically, essentially. There are these two vectors. Their linear span is the set of all linear combinations. Let me remind you what a linear combination is. I multiply this vector by a number, plus the second vector multiplied by a number, and then I add them together. I get some third vector. Then I take two other numbers. I multiply, add, and get another vector. I keep doing this indefinitely because there are infinitely many numbers that I can use to multiply these vectors. I simply take any numbers, and this is the set of linear combinations of elements. Each linear combination is a vector in this context. That is, in other words, in essence, fundamentally speaking, the set of these vectors comprises such a plane. This set of all vectors is essentially called the linear span. In this case, it is basically the column space of matrix A. So we have figured out what matrix A does to vector X. That is, when I multiply the matrix by vector X, I essentially end up in this particular plane. Having fully understood this, let's return to our equation and take a closer look at what is happening here. We need to understand the various components and how they interact with each other. Let this be the plane that is, which is officially and thoroughly, completely and thoroughly generated by the official matrix A in this context. The column space of matrix A. When I multiply the matrix by any two-dimensional vector x, I indeed end up in this plane. In this particular case, I have a vector denoted as x. Let's assume there is a coordinate system present here. This coordinate system can be used to represent the vector x in terms of its components along the axis. By doing so, in this example, I have a coordinate system displayed here. And in this same coordinate system, I have a vector labeled as x. Take a moment to carefully examine and understand the underlying issue. Identify the root cause and consider all possible factors. If only my equation looked like the very first system. This is indeed the very first system, truly the first system indeed. Truly. If it is rewritten in vector form, using the same notations, how does it differ from the second system? The issue is that there is no vector r here. In other words, I would essentially write it as x equals b. Can you actually tell me when this system would have a solution? Where basically should vector b be located for this system to have a solution? This is vector b. Where exactly should I place it in this specific context in order to ensure a solution for this system, to have a solution? This system indeed has a resolution if vector b also belongs to this column space, in fact. That is, if he were here, we would say that there exist two such numbers, the components of vector x. I multiply the matrix by vector x and obtain vector b. But since, as we have already established, there is no exact and precise solution, what does this indicate or suggest? This indicates that vector b does not belong to this column space. It is located somewhere outside. In other words, it is outside this plane. Because we have this exact solution, here it is. X is b minus vector r. This means that vector b lies outside of this space. Do you understand this point? It's somewhere around here.
Want to become a great programmer? Subscribe to our Telegram channel.